Hi, my name is Oisín, and this is the presentation for the paper Algebras for Weighted Search, a joint work between myself and Nicolas. This is a paper about search algorithms, and modeling those algorithms using applicatives, monads, semirings, and semimodules. It's a pretty big area, and I probably won't be able to cover most of it in this presentation, but rest assured all the details are in the paper. That said, let's get into the main motivating question for this paper, which is how to express search as a monad. By search in this case, we're talking about non-determinism, so that is programs that might have more than one answer for a given question. We're interested in how to construct those programs algebraically, and then how to evaluate those programs, potentially ordering some answers before others according to some arbitrary metric. One such program is this one, which uses the list monad in Haskell to search for Pythagorean triples. The variables x, y, and z here are drawn from the ranges 1 to 10. A guard is used to ensure that they do in fact form a Pythagorean triple, and then that triple is returned. Here's the result on the right. Behind this relatively simple program, there are actually some pretty important theoretical abstractions like the monad and monad plus class, which enable programs like this and have been the subject of huge research in Haskell and functional programming more generally over the past few years. The issue is that this is not the only way to search. In fact, it's not a very good way to search. For one, it's depth first rather than breadth first. So if we wanted to extend the range of the search space from just 1 to 10 to all natural numbers, this would diverge. It wouldn't return any answer. It also doesn't give us any way to order the answers. So if we wanted to search for a certain kind of Pythagorean triple, we'd just have to do a linear search and there would be no more efficient answer. Now there is a monad which allows us to do breadth first search. It's been rediscovered a bunch of different times and it's often called a levels monad. We're going to represent it here as a list of bags, where bags are sets that allow duplication. As you can see, it does indeed perform breadth first search. This is the same program searching for Pythagorean triples as the previous one that we had, except that the natural numbers being drawn from are all of the positive natural numbers, not just those in 1 to 10. And you can see on the right here that it does indeed produce a result without diverging. So if depth first search is the free monoid, then what's the levels monad? What about it gives us breadth first search? And that's actually the first question that our paper seeks to answer. We want to give a theoretical and an algebraic background and basis for the levels monad. We want to explain it to the same extent that we understand the list monad. Then we want to generalize this algebra to weighted search. We want to show that the levels monad is actually just a special case of weighted search, and then we want to implement an efficient monad transformer for this generalization. And we want to use this monad transformer to implement algorithms like Dijkstra's algorithm or the Viterbi algorithm and so on. So let's talk about the theoretical basis for the levels monad. This is only a small selection of the background. As I say, it's been studied numerous times. But let's talk about what it does mechanically. Fundamentally, the levels monad does diagonalization of its input, which means that from these two inputs, this is the pattern of pairing that it produces. You can notice that the level of each pair in the output corresponds to the sum of the levels of the pairs in the input. So if you look at 2C here, 2 comes from level 1 using zero-based indexing, and C from level 2, you add those together, you get level 3, which is indeed where 2 is there. If you follow a depth first search pattern, this is the search pattern that you get on the left, whereas the levels follows the one on the right, hence the diagonalization. That pattern of diagonalization is actually the same pattern that you get from polynomial multiplication when you represent polynomials as lists of coefficients. That representation works like this. First of all, you multiply out the polynomial, then you arrange it in order of increasing exponent, filling in the missing exponents, and then those coefficients give you the entries in the list. This is the same, as it happens, as the levels monad when you set the type variable of the levels monad to unit. Because bags of units are isomorphic to the natural numbers, following this isomorphism where the empty bag is 0, single bag is 1, and so on. From this list of coefficients can be translated directly to a levels value, meaning that levels of unit is isomorphic to polynomials. In fact, what's really interesting about this is that the monad plus operations correspond to the polynomial operations. While this is an interesting observation, it's still kind of a superficial one, because while yes, levels of unit is isomorphic to polynomials, we haven't said anything about levels of A in general. In order to do that, it turns out that we'll need some more sophisticated tools, provided by this paper in particular. There, semirings and near semirings are given their categorical analogues, which allows us to show that levels is a polynomial in monad plus, not in the natural numbers, and is a polynomial over bags. That's about as deep as I can go on that topic in the time that I have. The rest of the details are in the paper. Next, let's talk about weighted search. This generalization is going to be pretty simple. The levels monad ordered its search by the exponents on the polynomial that it represented. So to generalize, we clearly have to generalize those exponents from natural numbers to something else. That something else is the subject of this section. We want to figure out an algebra which properly encapsulates the notion of cost on a search. Take this graph, for example. It has 4 nodes, A, B, C, and D, and the cost, or the weight in each path, is x, y, and z. The first thing we will want to be able to do is construct new paths by joining all paths together. This tells us that we need a way to combine costs. So it should have a binary operator like this, or this. Secondly, we should know that any node that you're at, you should be able to stay there. There should be a trivial path to that node, and it should have a 0 cost. So these things together tells us that the cost should probably be a monoid. It should also obey some pretty straightforward laws, like for instance, the 0 cost should be cheaper than anything else. Or this one, if it's cheaper to go from B to C than it is to go from B to D, then it should also be cheaper to go from A to C than it is to go from A to D. For our work, we're going to use the Monus algebra to encapsulate costs. It's perhaps a little bit more restrictive than it needs to be, but it covered all of the instances that we wanted it to cover, and the extra laws enabled some optimizations which we're going to use later on. The basis for this algebra is this relation. This is often called the algebraic preorder on monoids. X is less than or equal to y if there exists a k such that x added to k is equal to y. Put it another way, k is the gap between x and y, and if such a gap exists, x is less than or equal to y. We can see straight away that the 2 laws that we had on the previous slide are satisfied by this relation anyway. These are just additive proofs of the statements. There's no need to understand them here. They're just here to demonstrate that this is relatively simple to formalize, and indeed it is in our formalization. So this is the definition of monus that we're going to go for. A monus is a commutative monoid such that the relation defined here is both total and antisymmetric. This is what we think of as costs in the paper. Some examples of monuses include the natural numbers under addition, rational numbers under addition, and also interestingly probability under multiplication. That last one in particular is what enables us to do things like the Viterbi algorithm. In the paper itself, we actually generalize this further from monuses to semirings in general. A monus itself, of course, forms the min plus semiring under some conditions, and it turns out that the search monad is a free semimodule, which means that it doesn't just encapsulate things like the levels monad, but also probability monads and sets and bags and so on. More details about that can be found in the paper, but for now we're going to move on to defining the monad transformer. This is the monad transformer for weighted search that we're going to use to implement Dijkstra's algorithm. We're going to start with a free monad. This is just kind of a shortcut way when you're defining a monad to make sure that it's definitionally law-abiding. So we're going to start with the free monad plus. This is a free monad, but at every level it's wrapped in a list. Algebraically speaking, this is the free near semiring. From there, we can turn it into a transformer by swapping out the lists with the list transformer. And from here, we can turn it into the heap monad, which is the monad that we're going to use for weighted search, by swapping out the functor for the writer monad. That W there is going to be constrained to be a monus in all of the algorithms that we're going to use it for. The main algorithms that we're interested in working with are graph search algorithms. In order to represent them using this monad, we're going to first need this combinator. This adjoins a weight to a pure value, returning the heap monad. Using this, we can represent graphs as adjacency lists. For instance, this graph on the left with the nodes A, B, C, and D, where the edges have weights in the natural number Monus. For instance, the edge from B to D has a weight of 2. That graph is represented on the right there in the graph function, which takes in a node and then returns a heap monad computation of the adjacent nodes, each of them tagged with the weight it took to get there. From here, we can actually implement the clean star. This should give us transitive closure of a graph. And indeed it does. When implemented directly on the graph above, we see that the transitive closure from A gives us the graph in this diagram here. You see that on the top level, you have the A value itself. Then, under a depth of 3, you have B, which under a subsequent depth of 2, you get to D, and so on. So this is how we represent graphs in the paper. So now we're able to properly describe graphs, and we have a monad that properly describes weighted search over those graphs. The last thing that we need is a way to evaluate those monadic expressions efficiently. And in particular, we need to implement the heap operations on this monad efficiently. The most important heap operation is pop-min, a function which removes and returns the lowest valued element in the heap. In our case, it's going to have this signature, which is a little bit strange because it has a monad wrapping and it returns a list of A's rather than just an A, but it is useful to implement things like Dijkstra's algorithm. The question, though, is can this be implemented efficiently? Remember that we started with a free monad, so everything here is still quite unnormalized and quite unoptimized in form. However, by a kind of a happy coincidence, it turns out that this heap structure that we have here is almost exactly the same as a pairing heap. So much so, in fact, that it's possible to implement the pairing heap merge on this heap structure that we have, meaning that this pop-min-t function can be implemented with the same standard complexity that the pairing heap has. And finally, we're able to implement Dijkstra's algorithm using the search monad. First thing we need to figure out how to do is to cross off nodes that we've seen already so that we don't search from them again, going into an infinite loop. Happily, since the search monad is a monad transformer, we can just layer in a state effect that does that for us. That's exactly what the unique function does. It keeps track of a set of already seen nodes, guards to make sure that the node that it's given isn't in that seen set. If it's not, it updates it, adding it in, and then returns it. Using this, Dijkstra's algorithm is just the following function. While there are a handful of combinators in here that you haven't seen before, they're all very straightforwardly derived from pop-min-t. So that's the end of the talk. There's a bunch more stuff in the paper like hyperfunctions and logic T, which I couldn't even mention here, so do give it a read if you get a chance. In the meantime though, thank you very much for listening.